Now let's attach the classification layer, which is we have to flatten those convolutional images layers, and we have to attach a fully connected layer on top of it to classify it. So for that, let's add model equal nb dot flatten. Input is model, and that's it. And after we add the flatten layer, we'll attach fully connected layer, which is we add the dense layer, attach dense layer, and the input is model. The output size, first hidden layer of the classification layer will have, let's say, 200 neurons, and let's add a summary variable as true, summary true. Okay, so these things are not required. I just had a habit of adding this again and again, sorry for that. Okay, so we have one fully connected layer. Let's add another fully connected layer, and let's have it with 30 neurons, and at the end, which will be the last output layer, it should only have the number of classes that we want to identify. So for this case, we want cats and dogs, so it will be only 2 classes, so we want only 2 neurons, so the output here will be only 2. And that's it. This is our entire neural network. It looks pretty simple, but actually lots of things are going in the background. If you remember, while we had in the last tutorial, we added all these functions which is doing all this work for us, and we get to then those functions made our work very easier. So we will use this. I want to create another name called prediction, and I want to make it equals to model. So the output of this model is now connected to this variable called prediction. So we will use this to predict our output. Now this was our network. We also need to attach our optimizer and a so we also need to attach an optimizer which will train this network. So for that, let's create an optimizer with tf.name scope, as I will put optimizer as scope, sorry for that, as scope. Before we move forward, I forgot to add one more thing. After each convolutional layer, we should add one transfer function so that our network becomes non-linear. We have created some transfer function here, so attach ReLU, attach softmax, attach sigmoid. So we will for the convolution layer, we will attach ReLU after each convolution layer. So for that, you have to do only attach nb dot attach ReLU, and inside that we only need to supply the so I'll just add this after each and every convolutional layer. Otherwise our network will not train will not be able to understand complex structure. It will become linear, and which is not very good. So we have attached non-linearity in our networks, and here also in this case I will add, instead of ReLU I will add sigmoid. Attach sigmoid. So this is just based on experimental value that sigmoid works better in fully connected and ReLU works better in convolutional layer. And the end of the network, where we have the output layer, I want to add one softmax function. So that is it. Softmax function is best when you are doing a classification problem. So we have our network ready now. Let's create our optimizer. So for the optimizer, it's best to create a global iterator counter, which will keep counting the number of times that our network has been trained. So for that we can use one and I equals 0, like this one. It will also be a counter, but the moment we stop this program and we save the model, we run it again, this I will again be 0. But we don't want that. We want to keep the counter from wherever it was in the when we stop the training. So instead of putting a local variable from the Python, we'll create a node inside the network which will hold the counter, and when we save the network, that data will also save, and when we pull back the network for retraining, it will start from that counter will start from the same. So it will not put any value in our training, it will not improve our training or anything, but it will show us that we'll have a parameter, so which will tell us how many times the network has been trained. So that will be good for us. For that, let's create a global itr iterator equals tf dot variable, and the initial value I want to set it as 0, and the name, let's put it as a same name, global itr iterator. And we don't want the optimizer to modify its value because it's a constant and it will only count the number of trainings. So what we will do, we will make this variable as a non-trainable. So our optimizer will not try to change its value while modifying all the other parameters in our network. So trainable equals, we'll put it as false. So this will be our counter, and now let's put a node where we will store our error rate. So we'll call it cost, means how much error there is in the network, equals tf dot nn dot soft max cross entropy with ledgers. So we are going to use this one to calculate our error rate. So this is a cross entropy, means this works best when you have a classification based problem, and for this you can have the softmax at the end of the layer. Here what we have to supply is, we have to supply the model, and we also have to supply the targets, where we are putting the targets. We have to supply the output of the model, which will be the prediction here, and we also have to supply the targets. So it will compare from the output and the targets, and it will give you the error rate. So let's put it as you can see the parameter for the output of the network is called logits, and the parameter for the targets is a label. So it is logits equals prediction, and lab label is equals to target. Let's name it as soft max cost function. Okay, so we have our cost function, and to tell the optimizer that we want to reduce this error, we can tell the TensorFlow like this: tf dot, so we can supply reduce min, and we will supply the what to reduce, which will be the cost. So it will reduce the cost, and this is our optimizer. So this is our cost in the reduce min, just ignore, and let's put it in the summary so that we can understand, we can see what is the current error rate is happening while training the network. tf dot summary dot scalar, and we will put the cost here. Now we are ready to create the optimizer. Opt optimizer equals, it will be tf dot a tf dot train dot, we are going to use Adam optimizer. We will supply the, will tell the optimizer which parameter to minimize. So it will know that to train the network, to know that it has successfully it is going in the right direction, we have to give the loss here. So in this case the loss is our cost parameter, cost function. So the output of the cost function. So this is the cost, and now the optimizer is knows it has to reduce this value. So to reduce this value, what it has to do in the network, what it has to manipulate in the network, that it will decide it on its own. So now the minimize cost, and we also now here we will supply the global step, global step, and this is this global iterator comes. Now that's it, we have our optimizer ready. Now it's ready for training.